So I think we could start. Good morning, everyone. Thank you for coming again. Just like the other days, we have a video from Dan. Today, Dan is reflecting on Bose-Einstein condensation and his relationship with the person he was an advisor. And afterwards, we have John Doyle, president of the American Physical Society, talking about to us. And later we have two talks from colleagues here. So I start the video from them.
To Bose-Einstein condensation. I guess I'm just going to start with the most fundamental question. What is it? And how was it that your research interest turned in that direction?
Yeah, well, it's a good question because that was the question I asked Tom Graytack. There was an article published in the Physical Review Letters in April of 1976 by Lou Nosenow and Bill Straley, and it pointed out the possible Bose-Einstein condensation of spin-polarized hydrogen. Well, I read this article, and what it pointed out was that if you have hydrogen atoms which are spin-polarized, which means the electrons in the two atoms point in the same direction, these can bounce off each other, these atoms, but they will not form molecules. And so they form an atomic gas, and that atomic gas has unusual properties. Namely, you could cool it to absolute zero temperature, and it would still stay a gas. It would never condense. Okay? Now, the reason that was interesting is if you can cool atoms, you can get them cold enough, but at high enough density, they undergo what's called this phase transition, the quantum mechanical phase transition, the Bose-Einstein condensation. And what it means is that you have a gas of all these atoms moving around like individual particles, and all of a sudden they change their phase. Well, I shouldn't say all of a sudden. As you cool them down, they start dropping into the lowest energy state in the system. They stop behaving like individual particles. It becomes like one giant quantum system. It's one quantum system which has many particles in it. The easiest way to describe it is they just come to rest. Now, they can't be actually at rest because of the uncertainty principle, but they go into the lowest state which is available. And this article pointed out that you might be able to see this. Now, this had never been observed in a gas. And I read the article, and I thought it was what they were requesting was kind of preposterous. It meant hydrogen at much lower temperatures and at higher densities than had ever been seen before. So I thought it was a very unrealistic proposal, and I was kind of annoyed at my friend Bill Straley for making such an outrageous suggestion, at least without saying, well, this is an outrageous suggestion, but they didn't discuss that at all. They just showed the science. Well, I had a conversation with Tom Graytack. Tom's background was in low temperature physics, was in liquid helium, studies of liquid helium. And he asked about that article, whether it might be possible to do that. And I said, no, that was totally absurd. And he said, well, that's unfortunate because Bose-Einstein condensation is really quite interesting. And I asked him, what is it? Just the question you asked. And he explained it to me. And so we had a series of conversations in which they would start out by pointing out why you couldn't do this and then figuring out a way why you could do it. And I realized that some of the techniques which we used in making the hydrogen maser, namely storing atoms in a vessel, might be applied to make spin polarized hydrogen to get to Bose-Einstein condensation. The art of storing hydrogen atoms in a vessel is to prevent it from sticking to the walls. And at room temperature, there are certain materials that hydrogen doesn't stick to, Teflon, for example. Well, in making the hydrogen maze, we'd often thought the ideal thing on the wall would be a film of liquid helium, because that's very non-interactive. Well, now we want to get to hydrogen at low temperatures, and so maybe the possibility was you could store it in a chamber with liquid helium, covered walls. And we thought of a very simple way of using a strong magnetic field, and so we started out playing with it. I mean, the first thing we did was just to see whether you could get atomic hydrogen, whether you could handle it at cryogenic temperatures. That had never been done before. So we started out just sort of playing around with it. It was one of the kinds of things you do in a lab just to, you know, it's sort of amusing. Maybe it'll lead somewhere, maybe not. So we didn't stop all the research to set out to see Bose-Einstein condensation, because the idea was too unproven then, but it was a clue that we decided to, you know, to pursue. So that's how the work started, and it turns out we could cool it down. A student who had just gotten his PhD and wanted to stay on to do some more research for a while, Bill Phillips, worked on these early experiments. I mention him because he later received one of the Nobel Prizes for developing laser cooling. And it turned out that ultimately laser cooling was a much better way to get to BEC. But at the time, he was interested in, well, he has a good taste. He spent some time working on that. So we were working on this and extremely enthusiastic, because when you start looking at what you want to get to BEC, it turns out that it looked to us like hydrogen was the ideal atom. Because of its low mass, it turns out it condenses at a higher temperature than any other atom would at the same density. And another thing is that the atoms did not interact. They're very much like ideal particles, which we thought was a wonderful advantage, but turned out to be almost a fatal disadvantage. So we started out, and we had we got a little seed funding. We got some seed funding. NASA was interested. There'd been proposals for using spin polarized hydrogen as a rocket fuel. I mentioned that when the atoms come together, if their spins are like that, they don't form molecules. But if you flip them over, they can form molecules, and they give out a huge amount of energy. So if you look at the energy per unit mass, which is a crucial factor for rocket fuels, it turns out spin polarized hydrogen is by far the best rocket fuel. I calculated you could make a Saturn V rocket, I think about maybe 15 feet high, if it were really fired by spin polarized hydrogen. But you can't do that because it just isn't stable at those densities. But anyway, so we were, I mean, NASA had done some studies, and they gave us some seed funding. And then as soon as we got our very first successes, that program ended, but we got other funding ultimately from the National Science Foundation to carry forward the project. Now, a few other groups got interested in this, particularly Ike Silvera and Joop Walraven at the University of Amsterdam, sort of independently started working in this direction. That Walter Hardy at UBC became very interested in the basic science of this. So we had a number of groups, and we learned a lot about hydrogen in the next 7 or 8 years. And then we came to a stopping point. We realized that at the densities we were aiming for, hydrogen would not be stable. So we needed to get a totally new approach to it. The idea of storing it in a bottle covered in liquid helium was not adequate. We had a very good postdoc working with us, Harold Hess, and with him, we thought of trapping the atoms in a magnetic bottle. Okay? But the question is then how you cool the atoms, and Harold had the wonderful idea that you could cool them just by evaporation. Namely, you could think of these magnetic fields as making a potential well, sort of a hole in the ground, if you like, where all the atoms are kept by gravity, only it's magnetic fields. If you lower the fields, the very fast ones escape, and so the average energy is lower. So you very carefully lower the fields, and the temperature goes down and down and down. The nice thing about this is that, in principle, there's no limit to the low temperature you can get. For ordinary refrigerants, as you pump away on them, their temperature goes down, and so does the vapor pressure, and at some point there's just no more particles coming off. But in this forced evaporation, in principle, you can go down arbitrarily far. So we started working on that principle and did trap some atoms. This was about 1988 or so. The problem then that we had to face was how to know what the atoms were doing. Up until that point, the way to know that you had trapped atoms was you start them flipping and they all burn up, and you get a lot of energy coming out. And that's a very nice big signal, but it's rather destructive of your atoms are gone, and there's no way to look for Bose-Einstein condensation. And we decided to use laser spectroscopy to see the atoms. Now, I mentioned in many respects hydrogen is the ideal atom, but experimentally it's a very awkward atom. It's not easy at all. In fact, it's rather heroic to be able to see the atoms using laser spectroscopy. So we set out on a program to do that, and that was hard work. Meanwhile, Bill Phillips and some of our other friends, Steve Chu and Claude Cohn-Tanucci, who all received the Nobel Prize for the accomplishment, I think in 97 or 98, invented laser cooling. I should say others were working on laser cooling too, but I think the prize quite properly went to them as playing the principal role in this. This gave a totally different way to cool atoms, and not hydrogen atoms, but other atoms. And at first, those experiments were, they seemed kind of interesting and amusing. It took a couple of years for people to realize that they might work well enough to get to Bose-Einstein condensation. So the race was on for Bose-Einstein condensation using the laser cooling methods. Meanwhile, we were working away in the lab on with our experiments. But our experimental methods, by any objective standard, were not very good, very complicated. These low temperature apparatuses are extremely complicated. The laser system was complicated. There was nothing elegant about what we were doing, but that's the way nature took us. So we continued on working on that. And I must say the students who were working were wonderful, because the experiments were very frustrating. If you get a leak in your dilution refrigerator, which happened now and then, it would be at least 6 months to really warm the system up, diagnose the leak, fix it, and get back into business. It's a very awkward technique. And but we had some wonderful students, and they were very tenacious. Well, in 1995, Bose-Einstein condensation was discovered. First, I guess in June at Gila in Colorado by Eric Cornell and Carl Wyman. Well, Carl had been an undergraduate in my laboratory here. He started in his freshman year, and he was sleeping in the laboratory in his senior year, either out of love of physics or desire to save rent. But anyway, he was he was a terrific physicist as an undergraduate. Eric Cornell had been a graduate student of Dave Pritchard. I mentioned that Dave came with me to MIT, and he did very well and joined the faculty. So, you feel very proud of your students, but I sort of felt they kind of overdone things in this case. But it was a great success. They got it. And then a couple of months later, Wolfgang Ketterle, whom Dave had brought here to MIT, to work in this area, and then Dave stepped aside so that Wolfgang could get a faculty appointment. He discovered it too. So it was discovered. And it was a wonderful thing, and everyone who knew about it thought this is pretty exciting. No one, I think, knew how exciting it really was. But meanwhile, we were plugging on and feeling we were discouraged enough to stop, but we wanted to do it, and we had two students who really were exceptionally good, Tom Killian and Dale Freed. And I remember, because we were still being plagued by these breakdowns, and I felt so sorry for them because they were just working away and trying to get the thing going. And then finally, in '98, it did go. So we got to Bose-Einstein condensation and hydrogen. So we were obviously feeling very pleased about that. And there was a conference on the subject in Italy that summer at Verona, one of the Verona conferences. This happened just before the Verona conference, and I reported on it there, and everyone gave me a standing ovation, okay, which was a very moving thing. But I realized that people knew that we've been working on this for over 20 years at that point. And I think it's kind of embarrassing when you have this group plugging away year after year. You sort of feel sorry for these guys, and it's embarrassing to feel sorry for people. Anyway, I think everyone was very much relieved, and we were certainly very much relieved to have finally succeeded in that. However, it turned out that although we did get there, hydrogen is not a good atom for studying Bose-Einstein condensation of quantum gases. We did pursue it some more, but then terminated the research because we were in a very different area of that world, and it wasn't going to be a really very productive area. So we finally achieved the goal after many years, but we didn't get there first. However, obviously you'd like to get there first, but it's a wonderful field, and we take great pleasure in having at least we helped put it on the agenda. It was because we were working on it that people started thinking about it earlier. So we helped. So we certainly contributed to the field. And Harald Hess's invention of evaporative cooling is widely used in the field. So we made some technical contributions to it also. However, I mentioned that no one really understood how much that field would grow, and it has been transformative, I'd say, in establishing a new relationship between atomic physics and condensed matter physics, and there are groups all around the world working not so much on Bose-Einstein condensation anymore, but what we call more generally on quantum fluids. There's two classes of gases: the Bose particles, and Fermi particles, and they have basically very different properties. Well, it turns out the electrons are Fermi particles, so many of the properties of matter depend on the properties of fermions, and one can study Fermi particles as well as Bose particles with it. So the subject now is just, it's still in the exponentially accelerating portion of the curve, and I don't think anyone would have predicted that.
I have a little bit of trouble understanding what it means that you have a gas that then starts behaving as one quantum system. Is there some way of explaining that to me that I would have any hope of understanding, and what the consequences of that are?
One of the reasons that the subject works so well is because there's such beautiful diagnostic techniques for looking at these gases. Not with hydrogen, but with these other atoms, the alkali atoms, you can actually photograph them. Okay? And when you photograph these atoms, when they are in, you keep them in a little trap, and it's rather small. You let them go. Well, they start falling, but they start expanding. Okay? And what you see when normal atoms expand is some go very fast and others go rather slowly. If you make a plot of the distribution of speeds, it looks like a bell curve. And that's what the photographs look like. They look just like Gaussian bell curves. Then you get to Bose condensation, and you notice that there is a little peak at the center. And then you go down far below the Bose-Einstein condensation, and you notice that the atoms are no longer expanding rapidly like that, that most of them are going very, very slowly. And the picture actually looks, you instead of like a broad distribution, you have a mountain wave standing out the center. Well, that wave at the center is composed of atoms which are in this single quantum state, and the reason that it expands so slowly is it's the minimum quantum state available. It has to have a little bit of energy, but that energy is just what the uncertainty principle says you have because you've confined them. So that's one way of literally seeing that the atoms are all in the same quantum state. I don't know whether that gives you good of
a little bit. Tell me also, again, a bit more about why this has been so crucial to, and why sort of studying this area is expanding exponentially. I mean, why has this been such a fundamental breakthrough?
Well, it's a fundamental breakthrough because it turns out that there are many theories from condensed matter physics which apply to these gases, but which you can study in fantastic detail, which you can't, if you're looking at, for instance, a phase transition in a solid. Well, one famous example is where the solid can go from being an insulator to a conductor. One of the theories of this, the very famous theory, the Anderson theory of localization, says that the reason that certain materials are insulators is due to disorder in them, so that particles which try to propagate as waves, the waves get scattered back randomly and they can't go anywhere. But at a certain threshold of randomness, they can start propagating. So you actually get a phase transition. Well, this is known. The theory is generally believed, but it's hard to study in very much detail because you can't really you can't change the matter. There's no knob to change from order to disorder in matter. Well, you can see this effect with atoms. Another development which has come along with these developments for laser cooling are methods for holding atoms with traps made of standing waves of light. Now that's a little bit difficult to explain, but if you have a standing wave of light like you do in a laser cavity, for instance, the atoms can be attracted or repelled by the field, and the field varies periodically in space. Now, those forces are very, very small, but at the ultra-low temperatures you can get to with these atoms, they can be large enough so that you can hold the atoms in these traps. Okay? And you can photograph them in there, too. So it's a very sort of a new world. And then you can start doing things. For instance, you can make the trap slightly irregular by shining other light on it. Or, if you want, you can turn down the trap. You can turn down the trap so that you just get one atom in each one of the little standing waves. Okay? It's almost like a crystal, but the atoms don't interact with each other. They're interacting with this light wave. Okay? Then, if you want, you can lower very carefully the trap a little bit further, and then the atoms do something permitted by quantum mechanics. They can start tunneling from one to another. when they start doing this, the system, which looks like a solid, suddenly becomes a liquid. Okay? They can flow. And you can see this, and you can study it with great accuracy. This is something you could never do before. So you can see these fundamental theoretical predictions in matter. You can see them under controlled conditions, which you could never see before. Furthermore, you can create new structures which don't occur in nature, but which you can make on your own. It's not only just being able to make them, but to be able to control things so accurately and to adjust them. One of the important properties of these gases is how much the atoms interact with each other. Well, there are now experimental techniques, so you can turn a knob and you can make the atoms repel each other or attract each other or not do anything to each other. So you can turn on and off these interactions. So it's a whole new world that's been opened, that's being explored both to understand the theories of matter, but also just to understand new or manipulate new types of quantum phenomena. I mean, everyone's heard about quantum computing, which is, still sort of a visionary idea, but experiments in quantum entanglement and quantum information theory can be realized using these ultra-cold atoms. So that's why I say no one dreamt of these things when BEC was discovered. Certainly not when we set out to work for it. We just, you just don't know. So, it's just a wonderful story of how rewarding science can be.
I also wanted to return to this question of mentoring, because although, as you said, you sort of ended up not being the first to achieve BEC, your students went on to sort of achieve things in other forms using other experimental techniques. And, to sort of have mentored and fostered work beyond just the work you were doing with your colleagues in the lab must be quite exciting.
Yeah, no, it's wonderful. I'm very proud of these students. So it's sort of nice to have had a finger in the pie of their education, if that's the right metaphor to use. Yes, certainly, and I mean, this is one of the reasons that one can take so much pleasure in science and so much joy in the achievements of others, too. I mean, it obviously would have been fun for us to get to Bose-Einstein condensation first, but I have certainly no regrets about not doing that. I'm delighted that it was discovered, and I'm delighted that the subject is is flourishing at the rate that it does. And it makes me feel very good about being a physicist, not just about Bose-Einstein condensation, but physics is a wonderful subject. It's an elevated subject. You look at the broad range of things being studied in physics, it's a great privilege to be part of that big picture. So it's been marvelous.
Okay. Okay. We have seen the last video of Dan. So, and now we have John Doyle speaking to us. John was a student. John, do you hear us well?
I hear you perfectly. Thank you.
Was a student of Dan and is now president of the American Physical Society. And he will tell us something about cold molecules, but also, I think, some of his time with Dan. Just before we start, Claudio Lenz was with us yesterday, and he asked us to say hi to you.
Wonderful. Thank you.
John, thank you a lot for accepting our invitation to speak to us. And please start whenever you are ready.
All right. Well, thank you. And thank you for the invitation to give this talk. It's quite a pleasure. Of course, Dan had a huge influence on the community and me in many ways. If nothing else, I always aspired to have his level of humor, which was really stratospheric. I enjoyed it very, very much, but also his commitment to public service, which I think some people know about, but he was really quite involved with this phase in American science where the idea was big science and little science, and Dan was, I guess it was actually called small science, was really a champion of small science, meaning things that can be done in a room, and had the power and the effects that those kinds of discoveries have, and articulating that the basic research, curiosity-driven research, cooperates with applied research, which then actually produces things for society. And of course, we're lucky to be in atomic, molecular, and optical physics, where that story can be articulated to the public. And really, Dan was incredibly inspiring on how to make those communications, but also that it was essential that we do that as a community. So I think you see my slide. This is just some pictures that you may not have seen before. This was the Kleppner-Hirschbach 90th at the American Academy. You can see on the left there was some chairs. There was actually some beautiful music there. And if you can see all the way to the right, holding the blue cane is Dan, and of course next to him, B. This was in 2022, so COVID was COVID restrictions were kind of ebbing at that time, and Conquina's knee is giving a talk, and many other people you might be able to see there. So I just thought I'd share just a few of these pictures. Here is Dan and B, of course, and Dudley with his chemistry wingman, and Dan with his chemistry physics wing woman. So it was kind of even. And there's poor B caught in the middle between physics and chemistry. There I am saying hello to Dan, and I think you'll recognize this picture, which is wonderful. So on the science side today, I'll be talking about ultra-cold molecules and spectroscopy for metrology-based particle physics. This is particle physics, which is increasingly successful at searching for new physics. As you know, there has been no new physics, particle physics found for some time now. The LHC and the methods I'll be talking about have searched. And we don't know what the microscopic nature of dark matter is. We don't know why there's a matter-antimatter asymmetry. And we have a hierarchy problem. And boy, we've had these questions for some time now. But I will describe how metrology-based particle physics really is a strong probe. But I also talk about the beginnings of AMO. And really the beginning of AMO was spectroscopy. And it started well before the advent of quantum theory, I would say the early 19th century. And through some technological advances, by just a few people, one was able to take light and figure out what wavelengths of light were made up, what was coming out of, say, a hot gas or a star. I have to really emphasize that there was the spectra were really very sophisticated in the sense that you could take any source, including from a telescope, and disperse them. And then looking at these lines, you could say, well, there's this material or that material in a star. Again, this is all 19th century, and this was now late 19th century, what you see here. But it's really quite amazing. And the ideas of atoms and molecules, and eventually at the end of the 19th century, the electron, all developed during this time period. And I have to say, the idea that the wave nature of matter in an atom or molecule kind of was invented in the 20th century is actually not true. In the 19th century, there were many ideas, because of the spectrum and the cadence of these spectra, that there was something resonant. There was some kind of wave structure inside, or vortex structure inside these things, which people had no really clue, really the details of, but that idea was there actually mid to late 19th century. It was quite developed. And this included for molecules. Now, just imagine trying to figure out what's going on when you don't really know what an atom or molecule is, and then you have some particular material from a chemistry point of view that gives some spectra. Sorting this out was incredibly difficult. It was truly difficult, and the spectra would change versus temperature, versus all sorts of parameters. Nonetheless, this was the beginning of our understanding of AMO. And all of that, the spectra were taken from this book, was just 1885, which is really kind of amazing. So we developed these ideas. We're able to do science, chemistry, lots of things without knowing the quantum nature of matter, but now we do. And we know this. Here's a very simple picture where we have an atom. We know that the energy levels of the electron around the atom are quantized, and you drive using electromagnetic radiation a transition from one quantum state to another. And that's what, this is the ideal thing, and this is how we understand this interaction. But of course, the reality is that the frequency of the light that you put in, that you need to put in to make this transition, will shift depending on the environment. And so the environment actually changes quantum level spacings. And one of the things, so that was certainly noticed right off the bat. But with the advent of coherent sources, we also had the idea of control, that we didn't just have a thermal ensemble of some of the atoms are in this state, some of the atoms are in this state, and we could drive the ones that were in the ground state up to an excited state. And some of them would go there. We can take a system, put them all in the ground state, and then at will decide when we want to drive the particle, the atom or molecule into the excited state. So this is the idea of quantum control. So you shine the light on for a fixed amount of time, it goes from the ground to the excited state. Now, of course, once that idea comes in, the idea of controlling matter, it's almost like a primal human thing to control the environment around you. And the next, one of the next steps, now fast forwarding many decades, was to have full quantum control, not only over the internal state, but also the external state. So you can take a particle like an atom, you can take a focused laser beam with the right frequency and hold that atom in free space. Then you can have two atoms. Now you've got control over a single quanta. You move to control over two quanta and actually show the interactions and start to control the interactions between these two individual atoms in these, what we call optical tweezers. And then you can do entanglement, quantum entanglement, accessing the magic part of quantum mechanics, if you will. Well, why stop there? As you saw in the previous talk, Dan mentioned about the visionary aspects of quantum computing. The things are really moving quite fast. The pictures I'm showing now are actually old. Things have advanced even beyond that, but you can see having an array of atoms, you have individual control over atoms, you're able to bring them together, you're able to make entanglement, and in a way that is doing useful quantum computations. So there's this progression from the spectroscopy, which we used to learn what matter was, to control of that matter on an individual quanta level, to now developing more complex systems, intentionally complex systems, which in a sense is a very far cry from when I started as a graduate student. Is, gosh, we wanted things as simple as possible. We wanted a single atom or a single molecule. We wanted to do spectroscopy on it for very good reasons. But now we have those reasons, which are precision measurement reasons, which Dan certainly championed, but also this new area of building intentionally complex quantum systems to study quantum many-body systems, which map over to materials, real materials, and also for quantum computation. So this is the AMO history. I've been using this now, this slide. I haven't changed the year, I apologize. This isn't the old version, but it gives you the idea how long I've been using this slide. at least 15 years, it's actually maybe 20 years, that we're in this area of controlled complexity or intentional complexity. And this is really the core of what we call the second quantum revolution, quantum simulation and computation, which is now a really significant part of AMO. So my group's strategy, if we have a strategy, this is how I like to talk about it, but we do with individual molecules. So I'm going to talk just very, very briefly about our quantum simulation and information work, just to give you a kind of a sense of where things are with ultra-cold molecules in this realm. So, oh boy, for people who worked on hydrogen, this is extremely scary. I worked on atomic hydrogen, but this is my life now. This is the simplest molecule that we deal with. It's a diatomic molecule. And on the left, you can see we're using a laser from the ground to the electronic state. It will decay, emit a photon, and that's photon cycling. If we can cycle enough photons, we can do this thousands of times. Then we can load a magneto-optical trap. We can get these molecules to microkelvin temperatures and do all the wonderful things, including holding single molecules in optical tweezers. Now, molecules are a little bit more complicated. They have these vibrational levels. So in very broad brush terms, what we have to do is repump these vibrational levels. What that means is that when it decays from the A state back to the X state, once in a while, this molecule will go to an excited vibrational state labeled by V = 1, N = 1 on the lower left there. But you get another laser, okay, costs a little bit of money, and then you repump that state. Repumps in atomic systems are common. With an atomic experiment, you have a few repumps. Here, with this diatomic molecule, you have a few more repumps. So it adds to the complexity of the light sources, although there's revolutions going on in lasers, and the complexity of the light sources is not something that we now think about. In the early days, we did. So we can take laser beams and focus them and make an array of focused laser beams. We can put one single molecule into each one of these laser beams. We can rearrange the molecules. We can bring them together and do computations. And the idea is really very simple. If you look on the right, you can project these laser beams through a microscope objective, and the molecules are held in these laser beams, and then you can image through the same microscope objective. So I'm going to go over this very quickly, a little bit for the experts in the audience. On the left, you can see we have individual molecules. You have this dipole-dipole interaction. And so you can define a qubit as a rotational qubit. That's in the lower left, where you have these two red states outlined. These are two different rotational states of the molecule. And then we label one rotational state spin up and the other one spin down. And now you can map over all the atomic physics that you know about spins and quantum computation to these two states. What you see on the right is a spin exchange, coherent oscillations of quantum information between two molecules held in these tweezers. And this is the first initial work. My group and a few other groups in the world did kind of similar initial work. And we showed a Bell state fidelity of 0.87, which definitely means that we have entanglement. It also is a very poor Bell state fidelity for those who always seem to ask a question, oh, well, how good of a quantum computer is this going to make? Well, we don't know. We're doing basic research. But this is a very interesting plot. So if we look at qubit platforms, on the bottom, you say, when is the year where these platforms first achieved single quantum state control? So ions were first. You have single ions with single quantum state control in an ion trap, then atoms, then molecules in 2020. But if you look at this plot of now two qubit gate fidelities over a function of time, the trapped ions made steady progress, superconducting qubits, Rydberg atoms made steady progress. The progress so far with diatomic molecules, once you have this initial gate made, is incredibly rapid. And I'm not trying to sell this as a qubit platform, but it brings in this idea that these molecules are more complex, which sounds really bad for a control point of view. But what it means is you can use these other internal states partially to tune away imperfections. And that seems to be what's going on in the field. Now, how far one gets with this, we don't know. But I will say there's a number of theory papers that expect 4 nines fidelity for these kinds of qubits. These are theory papers that predict that. So it'll be really, really interesting to see whether that little picture I painted, which is optimistic, comes true. But without question, the structure of molecules for quantum simulation are really quite different than the very simple systems that have been used so far. No question of that. We have rotational and vibrational states. They're natural spin-1 systems, some of these molecules. So I think it's a very interesting field, and I look forward to seeing how it develops. Okay, so that's all I'm going to say about quantum simulation and information. Now I'll switch to metrology-based particle physics, where I have to say, just right off the bat, we don't want interactions between these particles, at least not right now. The reason is because we're really just measuring precisely the spacing between 2 quantum levels in a molecule. And as I mentioned, what we're trying to resolve are 2 mysteries: dark matter and the matter-antimatter asymmetry in the universe. And I mentioned the hierarchy problem. I consider that a theoretical problem. But these 2 problems we absolutely observe the existence of these 2 phenomena, and we don't know microscopically why they exist. They are not explained by the standard model. Even though the standard model describes all lab-based particle physics, it doesn't describe these astrophysical observations. But there are lots of theories, very sensible theories, I have to say, to extend the standard model, adding new particles and maybe slightly different interactions with more, for example, time reversal violation. And I'll label these new particles X. See the big X in the bottom right. And we can try to detect these particles with a clock. Let me remind you about clocks. We have the mechanical clock, we have the crystal quartz clock. But really, one of the things that revolutionized thing was the atomic clock. And what you see is a beam type atomic clock using Ramsey interferometry. Of course, Norman was Dan's advisor and had a huge influence on Dan, as Dan has a huge influence on us. And the idea is you try to isolate these atoms, in this case atoms, these atoms in free space. Well, you do that by creating a beam in a vacuum. And then you interact with electromagnetic radiation. You do Ramsey spectroscopy simply to measure, in this case, the spacing between hyperfine states in a cesium atom. And that has become the standard of the frequency standard that's used, in fact, including these kinds of clocks are spinning around the globe in the GPS system that allows you to find your favorite restaurant or your way home from a strange place. The next level of this is to take atoms and make them ultra cold and hold them in these optical tweezers that I was talking about before. Now it's actually done in a lattice, which is a particular, we'll call it a particular kind of tweezer. And the idea again is you're isolating, you're trying to control the environment so that these levels don't shift too much, compared with, we'll call their perfect natural vacuum splitting. And then you make measurements by driving the system from the ground to the excited state using Ramsey spectroscopy. So that's how you measure spacings. You measure it in terms of frequency, which Dan would always say is that if you're ever going to do a precision experiment, you always want to turn anything that you're going to look for into a frequency, because we can count frequencies. And so if these new particles that explain the matter-antimatter asymmetry, that explain dark matter exist, they absolutely exist inside your body. There's no question that they're there because you have charged particles, you have electrons and protons. And the field around the electrons and the protons, the electric field, has energy. And so you can spontaneously produce particles, all kinds of particles, including positron-electron pairs, which gives rise to the G-2. So if there's a new particle X, it will be in the vacuum. virtually. And we can think of that as, first order perturbation theory, or on the bottom right, which is just this Feynman diagram, which shows that you can create and annihilate this particle X. That phase on the right, that F e to the I phi, that phase is a time reversal violating phase, which is generic in all of these beyond the standard model theories that are being thought about. So remember this plot, the idea was if you had a system with two quantum levels and you had the environment perturbing it, it would shift the frequency. Well, the environment can be this new field, this particle that might exist. And I'll explain how we can get at that. A little bit more technical. We have, again, this is a single loop diagram showing the CP violating phase, kind of in the middle on the left, it's e to the I phi CP. This particle, this proposed particle that's in this diagram is the selectron, the supersymmetric partner to the electron. And then the mass of this beyond the standard model particle, lambda squared on the upper left, can be written down in terms of this phase and the electric dipole moment of the electron. In other words, if you have these new particles, these beyond the standard model particles, and they have CP violating phase, which again is generic, they will produce a low energy effect, is that the electron will not only have a magnetic moment, it will also have an electric dipole moment. And so we're going to use spectroscopy to look for the electric dipole moment of the electron. Now, the theory is that the standard model actually predicts an EDM. It says, okay, there will be an electric dipole moment of the electron at a certain level, but it's many, many orders of magnitude lower than current experiments. So if current experiments find an electric dipole moment of the electron, it will be due to a new particle. And then if we find that, then by doing this experiment on multiple systems, we can learn more and more about the nature of that particle. So we do an experiment called ACME. It's a collaboration between Harvard University, Johns Hopkins, and Northwestern. I was just hesitating because the two other faculty members had moved a couple of institutions in the meantime. And then we also collaborate with Caltech and Okayama University in Japan. And so you can see that on the left, what we do is we take a molecule, thorium oxide, and inside that molecule is an electron. And the thorium oxide molecule has a very high internal electric field. So if I'm able to arrange, keeping the electron spin fixed in the lab frame, but then change the direction of the molecule, flip the molecule back and forth, then what I'm doing is I'm flipping the electric field back and forth. And that means that the shift in energy of the electron due to the interaction of the electric field with this with the electron electric dipole moment, or the purported electric dipole moment, I'll see a shift in frequency depending on which way the molecule is pointing. What frequency? You guessed it. You put the electron in a magnetic field, it'll be processing around at some frequency. And then as I switch this electric field back and forth, that frequency will go up or down if there's an electric dipole moment of the electron. So here's the experiment. It is a beam experiment. So we create cold thorium oxide molecules on the left in what's called a CBGB, cryogenic buffer gas beam. But from that point forward, in broad terms, it's just like the cesium clock that I pointed out previously. However, we use all the modern AMO tools to do this, and I could wax poetic about that for some time, but I won't today. So we, this experiment ACME, put a new limit. What you see in the y-axis here is the time of when the experiment got the result. On the x-axis is the limit for the electric dipole moment of the electron. We have not seen that yet. But then also laid on top of this are all the theories beyond the standard model theories that predicted an EDM. And what you'll see is we made 1 order of magnitude improvement going from 10 to the minus 27 to 10 to the minus 28 in 2014. And then we made another order of magnitude experiment in 2018. And you can see the theories that we've highly constrained is the polite way of saying it, but really have ruled out with a very high degree of probability. And this includes theories that were really extremely popular and I have to say extremely well motivated. When we started this work, there was very, very good motivation for this idea of SUSY, what we call natural SUSY. But clearly that's not the case. If SUSY exists now, it's going to be unnatural, or it'll be some kind of variation of that. So right now, what we're doing is we're intersecting with a number of new theories, some that came before the LHC, some that came after the LHC. And we're currently working on ACME. I'm going to skip this because it's a little bit too technical. We're currently working on ACME now. I'll just show you this plot. We're working on ACME 3 now, so we expect another order of magnitude within a couple of years. I'd like to kind of put this in context of experimental particle physics. What you see on this plot is the limit we put on the electric dipole moment of the electron, but also compared with the energy that the accelerators are able to reach. So let's start with the accelerators. You can see over time they've increased, but then that increase flattened out quite a bit versus year, and really the LHC is kind of pinned to around 1 TeV for direct production of these particles X, these particles that we think should exist for matter-antimatter asymmetry and dark matter reasons. Then on top of that is all the EDM work, and you can see now with THO, and now the best measurement is being done. Last best measurement was done by Gilla with a related molecule, hafnium fluoride, is now above the probe level of the LHC. And what I mean by that now is a very technical statement, but that's not one loop, that's 2 loop. So even at 2 loops, which is a very, very broad probe of new physics. So we are sensitive, for example, to the supersymmetric partner of the top particle called the stop. At 2 loops, even in 2 loops, it's now in the 3 to 10 TeV range, probing for new physics using the electric dipole moment of the electron. So it's quite an exciting time. Here's ACME 3, on the right now, we just flipped direction. On the right is the CBGB creating the molecules, and on the left is that Ramsey interaction region. You'll see with ACME 3, we have a much, much larger signal than ACME 2 and ACME 1. This is all due to the work of very dedicated graduate students, and it's been going very, very well. We're now currently running ACME 3 with about 30 times the EDM sensitivity. What you have listed here is just showing where the improvement came, how we got this sensitivity. It's a number of quote, small improvements in various parts of the experiment, including just simply using better detectors. This is a fun thing. This is where we obviously staged it, but this was true. We were setting the blind, so we blind the EDM channel so that while we're doing the precision measurement, sorry, excuse me. So while we're doing the EDM measurement, we're not influenced to say, okay, are we going to try to get the same 0 or non-zero? So we put a blind, a random number blind. And what you're seeing there is where Dave DeMille and I are clicking the button and setting the blind and having a whole lot of fun doing it, because this is the only button I think that either of us have actually touched on ACME 3. All the work is done by the graduate students and postdocs. And this is where we project to be for ACME 3. And here's the crew, the current crew, what we call on the ground. It's a very complex experiment, and it's amazing that this number of people can run it. So what's the future of EDM searches? I hope I've convinced you that there's a good reason for doing it, and we're continuing to do it with ACME 3. But if we wanted to get more sensitive to CP violating physics, we want to be able to either increase our coherence time, increase our count rate, or increase the inherent sensitivity of our system to CP violating physics. Those are our choices. And of course, we always try to work on anything we can to improve the sensitivity to the electric dipole moment. But I mentioned about optical tweezers. I mentioned about optical trapping, and the best clocks, which are essentially, an EDM experiment is just a clock, except that you switch the direction of the molecule back and forth to look for the EDM. So that's what metrology-based particle physics is all about. That's why we call it metrology-based, because we're essentially using clocks in some way. And so the best clocks are these optical lattice clocks, putting ultra cold atoms into the optical lattice and measuring these quantum state differences using spectroscopy. And so what we'd like to do is put these molecules that have these properties that are sensitive to EDMs into these optical lattices. And we also want to have the structure that you saw before with thorium oxide. Turning that molecule back and forth actually uses a structure which we call an omega doublet, which has to do with orbital angular momentum along the internuclear axis. And so one can use a very special molecule like thorium oxide or hafnium fluoride that was used in the Joule experiment, diatomic molecule, but those are extremely rare. They're very special that they have this omega doublet structure. But if we go to more complex molecules, that orbital angular momentum becomes generic. That if you have, in the upper left, you have K, which is a quantum number for a symmetric top, where the symmetric top is spinning around the internuclear axis, or below that, little l, which is if you have a bending mode, a vibrational bending mode in a molecule, that can give you orbital angular momentum along the internuclear axis. And so you can see that that gives you a structure if you apply an electric field where you have one quantum state with the molecule pointed up and another quantum state with the molecule pointed down, which is exactly what I showed with the thorium oxide. So there's ways of getting this very desirable structure for doing EDM experiments generically in molecules. But you need polyatomic molecules. So how do you cool polyatomic molecules? There's one way to do it, we think, and I'll show you that we can do, is by laser cooling. And this requires a little bit of thought. You want to get a molecule which, that has an electron in the outer orbital, a single electron, that acts like an alkali atom, that acts like Dan Kleppner's favorite atom, the hydrogen atom. As I think Dan said, the alkali atoms are the poor man's hydrogen, because they're easy to access technically. So you can look at this paper about the basic approach, but the bottom line is that you can find these kinds of molecules. And now I will summarize 15 years of work in one slide. You can put a lot of effort experimentally, but eventually you get a system where you can do laser slowing, you can create a MOT, you can create subdoppler cooling, you can put the molecules in an optical dipole trap, and then eventually into optical tweezers. This was done, we did this all with calcium monohydroxide. And so calcium monohydroxide is a polyatomic molecule. You can look on the left, there's a little, it's vibrating, that's what's called a bending mode, and that's the bending mode that gives you this orbital angular momentum. You can see it's on the lower left, each dot is a single polyatomic molecule, and they're all the other usual kind of things that you can do with ultra cold molecules now are done with calcium monohydroxide. And we've now been studying calcium monohydroxide. We've now been studying calcium monohydroxide. Actually, we're interested in this for quantum information purposes, and we've gotten quite far. But I like to focus on the EDM here. So here the idea, there's a lot on this plot. So I'm just going to summarize it in a few sentences. Right in the middle of the plot, you see a polyatomic molecule in a bending mode. This is a mode where it's bending, excuse me, as was in this animation on the upper left. And what Nick Hutzler at Caltech and his graduate student Yuiki Takahashi and collaborators showed theoretically is that amazingly enough, one can take this molecule and put it in an electric field and tune it so it's nearly ideal for looking for an EDM. You can tune it so it has a zero magnetic moment in the lab frame, which means it's insensitive to variations of magnetic field, which would of course shift these frequencies that we're trying to measure so precisely, but still have this structure which allows switching the molecule direction back and forth and still have sensitivity to the electric dipole moment. So this was really an amazing finding that they made. And before moving forward, we have to talk a little bit about quantum numbers. Most people who work in AMO don't know about these quantum numbers because it's not usually taught, but there's different vibrational modes, and you can see, we write these down as in these kinds of molecules. We have different nomenclature for other kinds of molecules. That's the way chemistry is. Where you have the stretch mode for the dominant stretch mode on the left, then you have the bending mode, it's the middle quantum number, and then on the right is the other stretch mode for the light atom on the right. And you can see on the right where you have a bending mode, you can have orbital angular momentum of the vibrational bending mode, and that's what you're seeing with this quantum number, which is a superscript. And so we're able to show with calcium monohydroxide the protocol that was predicted to work for triatomic molecules to look for the EDM. So we have this EDM state. All we're doing in this experiment, you see where the EDM state is in the upper left. We have m equal -1 and m equal +1. That's the orientation of the electron. And so we put the electron in a superposition of +1 and -1, which means you tip it off on its side, it precesses around, and then we measure that precession. And that precession is depicted in the lower left as oscillation of a state, of one of the states as a function of time. On the right, we actually show that we're able to tune to this magnetic field insensitive state. So calcium monohydroxide, however, is not sensitive to EDM because calcium is too light. I didn't go over that, but you need a heavy atom for it to be sensitive. However, you can see in the table, strontium monohydroxide is sensitive, barium, ytterbium, and all of these have the same, they're isoelectronic to calcium. So this demonstration experiment really shows, kind of the pathway to doing better electron EDM experiments. And that's depicted now on our theory plot as where we'll go. Can I ask how much more time I have?
More 10 minutes.
Okay, perfect, wonderful. For those who are interested in quantum computing, quantum information, we did this experiment very recently. It's submitted now, and referees are looking at it. What we've done here is, I didn't talk about this, but the way that we describe these two states, these states of orbital angular momentum, and these omega doublets and turning the molecule back and forth, that might be reminiscent in your mind to your early education with molecules. If you took a chemistry class, these are parity doublets. So that means that these two orbital angular momentum states shown on the left, the linear combination of those have opposite parity. And so these parity doublets actually are what gives you the ability to orient the molecule. If you apply an electric field, you mix these parity doublets and they become the molecule oriented in one direction or anti-oriented in that same direction. That's what parity doublets are. And what we've shown is a new type of qubit, which is parity doublet qubit. You actually are using one of those parity states as one say spin up and the other parity state as spin down. Why would you want to do this? Because all the other quantum numbers are exactly the same. The only thing that's different is parity, which means that if you have environmental changes in electric field or magnetic field or interactions with other atoms, whatever that might be that would shift these levels and give decoherence to this qubit, those will be highly suppressed because other than parity, The magnetic moment's the same. The electric dipole moment of the molecule itself is the same. Everything's the same. And what we've shown here on the right is a coherence time, a bare coherence time of a second. That means that we have the pseudo spin, this parity doublet pseudo spin, and we tip the pseudo spin over, and it processes for a second before it decoheres, which is really really exciting for us. And here's the team that did that work. However, there is a new sheriff in town. There's a new thing which was predicted theoretically by some very brilliant theorists, that one can use molecules that have about a factor of 1,000 times more sensitivity to CP violating physics, to EDM physics, than the electron. And what this is that you look for the electric dipole moment of a nucleus, but a very special nucleus. These are nuclei that are octopole deformed. And that gives you this enhancement to new CP violating physics. And the way to think about this, it's not so trivial, but I'll give it a shot. The way to think about this is that imagine a molecule. Now let's go back. I don't want to. Just imagine a molecule in your head. You have this molecule. It's in free space, and so what it means is that it must be true that the wave function is spherical, right? With no applied electric field. When I apply an electric field, just think of a diatomic molecule rotating around. What I'm doing is I'm mixing the opposite parity states of this rotation. Just like when I apply an electric field to a hydrogen atom, I can polarize the hydrogen atom by mixing two opposite parity states, the S state and the P state in atomic hydrogen. Now, an octopole deformed nucleus, you can imagine those two opposite parity states of the nucleus itself being mixed by parity violating, CP violating new physics. And so this octopole deformation, it's like a molecule, and the mixing term here is the new physics. And that's what's depicted on the right. And so it turns out, right, one more last thing, it turns out the energy splitting between these opposite parity states in the nucleus are actually very small. So if you can see this S term in the middle of the plot on the right, if you have a small splitting, that means in perturbation theory that you have a large effect. So this has given rise to trying to use the best tools we have for doing spectroscopy on molecules that have octopole deformation. And so at MIT, in the group of Ronald Garcia Ruiz, he's been working on this. He's a nuclear physicist, to create radium fluoride molecules and then do spectroscopy. And that's what you're seeing on this plot. It really, on the right-hand side, sums it up. You have these particular states, molecular states. They're depicted on the right, the vibrational states, the electronic states. And what you're doing is just simply spectroscopy, just like we did in the 19th century, in order to find the locations of the quantum states we need to laser cool and do the EDM experiment for the nucleus. At the same time, Nick Hutzler was working on radium monohydroxide, which is a molecule, again, you can put in a bending mode and has this property of these opposite parity states of the molecule, that we can orient it in the lab frame and do the kind of EDM work that we're used to. So he's been doing a lot of spectroscopy, but we need to eventually get them ultra cold and load them into an optical trap. And it turns out that radium monohydroxide is actually easier to laser cool than the molecule I've just talked about, calcium monohydroxide. This has to do with the particular bonding that goes on and what happens as you go to a heavier and heavier species, what happens to the orbitals, and you have this relativistic collapse of the inner orbitals, et cetera. But the bottom line is we're very optimistic. We can laser cool radium monohydroxide and put it into an optical lattice and do EDM experiments. So the three of us have formed a collaboration, which we call the RAX collaboration, where X stands for fluorine or OH, or perhaps OCH3, a methyl group. And this experiment, the RX collaboration, is very vibrant. We have now a new laboratory here at Harvard. You're seeing all the parts that we've been putting together, and even this is now old. It's gone far beyond this. So things are going quite well. To give you an idea, remember that factor of 1,000? To give you an idea of where we're going, you can see this line all the way to the right. We can cover all of the theory space you see and get actually all the way to the standard model. Now, we expect to see something before we get to the standard model. There's very good reasons to think that theoretically and experimentally, our observations of the matter-antimatter asymmetry and dark matter. But in any case, this tells you how much incredible sensitivity is predicted. And so we're very excited about this. Here's the team that's doing that. And I hopefully have the slide here. All right, I wanted to make sure we're not the only one who's recognized this. The entire field has jumped on this octopole deformation path for excellent reasons. That includes a new faculty member here, Xin Fan, who will be doing looking for the CP violating physics using octopole deformed nuclei actually in an ion trap. Now remember, ion traps, were one of the first first devices to have full quantum control over an atom way back, and the current the current best electron EDM experiment done at GILA is with an ion trap. That's hafnium fluoride plus, if you didn't notice. So there's two complementary ways of going about these precision measurements, just like there's two complementary ways of making a precise clock. One can do an optical lattice clock, but one can also do an ion clock. And they have about the same sensitivity. The optical lattice clocks are ahead by some order of unity right now. But that's the same with precision measurement. And so this complementary method, given the physics that's involved, is absolutely essential. And there's also ideas of using solids or other more exotic approaches. It's maybe you can't quite see it on the screen, but the physics reach of this method is well above the plot that I showed last time. Okay, and I think I'm going to stop there. Do I have 2 minutes?
Yes.
Okay. There's one other thing we can do with these ultra-cold molecules. We can look directly for dark matter. And the idea here is very, very simple. If there's dark matter, it permeates all of us, not virtually, but it's actually there. And it will interact with electrons and protons differently, which will give a different shift to their masses. It'll interact, so it's kind of like a sludge of which the electron or proton is moving through, and will add some mass to these particles. And so if we measure the ratio of the electron-proton mass, we are sensitive to dark matter. Now, how does the measurement actually occur? For dark matter, which is ultralight, ultralight dark matter is like a BEC, so you're in this field of ultralight dark matter. It will give a Compton oscillation, a Compton oscillation in time. You actually have this oscillation in time. Why? Because you have e to the I omega t, and omega has mass in it. So you'll have this oscillation of the electron to proton mass ratio, and that's what we're going to measure by measuring the oscillation in two different quantum levels in the molecule, which is the bending mode and a stretch mode. And so you can see on the right, we have this molecule SROH, and we pick these two vibrational modes. One's a stretch and one's a bend. And we'll simply measure the splitting between those two. Those are accidentally nearly degenerate, so we can do this in the microwave regime. And we'll measure that as a function of time, looking for dark matter. This turns out to be, on paper, very sensitive to ultralight dark matter. On the x-axis is the mass of the proposed ultralight dark matter, covering 3 or 4 orders of magnitude, and the sensitivity of our experiment compared with, in the dashed lines, compared to the current limits from other experiments. And so with about 1 month of data, we should be able to measure, to probe for dark matter more than an order of magnitude more sensitively than previous experiments. And I think that's it. Oh, I should just say, we have laser-cooled SROH, the molecule we're going to use. We have it in a MOT. We've put it in an optical dipole trap. We've found the science states, these vibrational states. We're able to populate them in the optical dipole trap. So we're now doing spectroscopy with an optical clock, so to speak, looking for dark matter in a polyatomic molecule. That's the team that is doing the work, and that's it. I'm just going to skip through. We're looking at much more complex molecules also, but I'm going to skip through all that. And here is the group. Thank you very much.
Thank you, John, for the wonderful talk. Do we have questions from the audience? So I start. Yes, I have one question before.
Thank you for this very interesting talk. Lots of very interesting results. I would want to ask two basic questions. So the first one is, what would be the main mechanism for creating electric dipole for the electron in the standard model? So what makes the electron?
Oh, great question. I have a slide because it's a great question. It turns out to be an unbelievably complex diagram. So it's a four-loop diagram that creates the EDM in the standard model. Now, that being said, the basic physics of it is very simple. That the CKM matrix, there is a CP violating phase, right? The CKM matrix.
Well, I know that there's some small violations, but I'm not sure about this CP matrix.
Oh, okay. So the CKM matrix is the matrix which relates the strong force mass eigenstates to the weak force eigenstates.
Okay.
And there is a phase in that. That's the CP violating phase that gives rise to the EDM. So we know that there is an EDM at some level in the standard model just because of that. It has to be true. But you don't know at what level of perturbation theory. And it turns out to be for loop. And this is due to what's called the GEM mechanism, capital G, capital E, capital M. And if you ask me what that is, I don't have an answer.
Okay.
It's now deep in theory land.
Okay, thank you. And I have a second question. So I imagine that from the point of view of the experiment, it's very hard to measure things with that kind of precision, but you are measuring something which is physically understandable, so the dipole of the electron. Now, when you jump to the conclusions, let's say at some point you want to claim that you have detected dark matter or etc. How dependent those kind of claims are on models, and how close do you collaborate with the regicians? I imagine that this is very hard to understand. What does it mean, your measurement, I mean?
That's the second great question. That's wonderful. So yeah, the way to think of it is the way to think of it is this, that the theory for molecules, right, even if it's like, it turned out to be accurate to like 20%. In other words, if I just give you a molecule, a simple molecule, I can tell you where things go, everything about the molecule, basically on the 20% level. Now, for very simple molecules, it's much more accurate than that. So whatever effect you're going to see, you won't know how to map it over to theory on the order of unity. Okay. However, you don't care, and let me tell you why. Because if you have an EDM and you don't know the actual value of the EDM within 20%, who cares? You have an EDM; it's not zero. And then, of course, you have to eventually compare with theory, but that changes the whole ballgame. You can use a different system, like a different molecule, or go to a nuclear EDM, and you should be able to see and figure it out from there. For the dark matter, again, you don't care. That's like a coupling constant. So you see an oscillation, right, then you know that it's going to be dark matter as long as your systematic effects are under control. But that's, of course, generic to all precision measurements. You have to do an enormous number of systematic checks to convince another scientist that you know what you're doing. In the end, it becomes kind of a scientific fact if you have two experiments that are fairly different giving you the same answer. And so the way I say it for our electron EDM experiments, like we had a limit for the electron EDM from the ACME experiment using the thorium oxide molecule I showed you. But I wouldn't, and we published that limit. And would I call that a scientific fact? No, I think it's a very strong result. We believe in that result. But then the Gilla experiment did the same experiment in a completely different system with completely different systematic effects and came to the same answer. And then I think it raised it to kind of a scientific fact that the electric dipole moment is less than some certain value. Does that make sense?
Yes, thank you for the answer. Yes.
Yeah, thank you for the question.
So I have a question. So we have recently seen Bose-Einstein condensate of dipolar molecules in the group of Sebastian Will. Do you think this new quantum fluid that it's dipolar and molecules will play a role on all this story that you told us?
That's a great question. When BEC first came about, I think Eric Cornell said it best. He said, I forgot whether it was during a question and answer period in public or it was just one-on-one. But he goes, you know, I'm beginning to think the most important thing about BECs is it's just cold. and it's kind of, it turns out to be, you know, this was whatever, when was BEC, 87 or something like, no, sorry, 90, 97, something like 95, something like that. It was actually a pretty good remark in that for precision measurements, you're going to get a very long answer because I think it's pretty cool. For precision measurements, what we care about is that it's cold. So that we can hold it, we can do quantum manipulation. It has small perturbations from the environment. We can hold it with very gentle light. The colder it is, the light that we hold it with is more gentle and therefore less perturbing to the quantum states, which makes a better clock. Also, we can do things like create arrays of tweezers with molecules and then potentially separate them so they don't interact. This is actually, right now, with clocks, Adam Kaufman is really thinking about this, that maybe these tweezer arrays are the best way to make optical clocks. So that idea is very much that we want isolated molecules, we want them cold as possible, and that doesn't really depend on BEC, except that you just want them really cold. So whether you get that through laser cooling, evaporative cooling, which I worked on as a graduate student, and or a BEC, it kind of doesn't matter. However, if you wanted to do quantum enhancement, if you wanted to do squeezing of these states in order to make more metrological gain through entanglement, you need interactions. And so you can think, there's a couple ways of getting interactions. One is you can put these molecules in a light field and couple them through a light field. And this is a standard way of squeezing quantum states in a gas of atoms, and this has been done. But you can also get squeezing through dipole-dipole interactions. So you can imagine that through the dipole-dipole interactions of the molecules themselves, these are the electric dipole moments of the molecules here we're talking about, you could actually do squeezing, and there's a number of theory papers about this. So you can imagine that you actually want a dense sample of molecules that are cold, like a BEC, in order to do squeezing, in order to do your metrology and your clock, make your clock better. And this is really, now I've really described to you the forefront of thoughts about how to make clocks better, thoughts about how to improve precision measurements beyond the quantum limit. When I say precision measurements like I've been talking about, that actually truly look at new physics beyond the standard model. So it's very, very exciting. And another great question. Thank you.
Thank you very much. I don't see further questions, so I'd like to thank you again for the amazing talk and the time to talk to us here today. Thank you very much, and I think we can all thank John again.
My pleasure. Thank you.
Bye-bye, John. We have a shorter break. I'll ask you to be back in 15 minutes. Okay, welcome back. We have now Professor Benhu Viana Borges. He is a colleague from the engineering school here in São Carlos, but he is also one of the leaders of the CUTIA program, which is the Quantum Technologies initiative from our state funding agency. Because as you know, there are nice things to be done, but we still need the money to do it, and someone pushing us to do it. So he is here today to speak about this initiative from FAPESP. Benhu, thank you a lot for your time, for coming to talk to us about this, and please, the stage is yours.
All right, thank you very much, Manuel, for the invitation, and thank you all for being here today. I'm going to discuss with you what this program QT actually means, and how long it took actually for us to come up with this concept, and to convince FAPESP that this is really something that it matters to the community here. And as you know, Brazil is actually lagging behind in terms of investment in quantum technology if you compare to the major initiatives in the world. And what we are trying is see if we can accelerate the pace so that we can, get a little bit closer to what people are doing outside. We already know that here, particularly in the state of São Paulo, that we have lots of fantastic groups and that are working for decades with quantum technology. And we know very much what people here in the Physics Institute are doing, which is quite amazing. And the idea is to take advantage of all the fantastic people that the human infrastructure, if we can put it this way, that we already have, and see if we can direct this investment in such a way that we can get research on the same level that we are seeing happening outside. We know, as I'm going to show you, that of course that some leading countries that like China, for instance, if you consider what they are doing, half of the investment in quantum technology is being executed in China, this globally. And but right now, I think Brazil, from a few years back to today, I think Brazil has a little bit picked up the pace, and we are actually seeing some very interesting initiatives like this one that I'll try to discuss with you and show some numbers that and future perspective for this initiative as well. And just to begin with, we know that, probably you guys know already, that the kind of money that we're talking about for Cutia is 150 million reais for the whole program. And with this kind of money, I think we are already doing some interesting call, as if you had an opportunity to follow what we are being publishing in terms of all the call for research proposals are available in the FAPESP website. All right. So okay. What's the basic idea of this initiative? We actually, you actually can see, this is the main topics or the focus of this initiative. We actually need to implement a better and more productive workforce dedicated to quantum technology. And there's one important thing. Even though there's lots of interesting research happening in all the physics institutes around the state of São Paulo, I'm not going to mention, I'm going to focus on the state of São Paulo. Well, the problem is what FAPESP intends for this kind of program is that the physics groups also approach groups in the engineering. Because you have to bear in mind that you not only need to produce new science, you also have to apply what you're doing. You have to make this thing get closer to industry, all right? Because this is very important. Otherwise, we're not going to make the quantum leap in terms of what we can do here. Right now, I don't know if you're following what's going on in terms of quantum applications outside. There's some kind of stuff that we cannot import because they don't want you, countries like Brazil, for instance, which is a potential competitor in the area, to have access to certain kind of quantum technology. Embraer, for instance, we are doing some stuff with Embraer. And there's some kind of sensors that even Embraer cannot embed in the airplanes. They don't have access to that. That has to be done somewhere else, in the United States or Europe. And this is happened actually because you do not have the technology. When you talk about quantum computer, we know there are a lot of groups in Brazil that are actually doing some stuff, some very interesting stuff in quantum computers. And we have a colleague of ours in Campinas, Rochinol, which is doing a fantastic job. But we're still not actually at the point that we can compete with what's going on outside. And right now, if you want access to some certain kind of computation, for instance, you won't have that. And there's something very interesting that happened in the workshop that we organized in São Paulo. Some groups here in Brazil was telling that they had a collaboration with a certain country in Europe, and the government of that country canceled the collaboration in order for that country to not pass the knowledge about the subject to Brazil. That happened in an ongoing project. So that is why, if we can not only develop new things here, but we have to bear in mind that the workforce, right, the PhDs, the postdocs, they are quite important in this thing. And we need to bring those guys back. And this is one of the purposes of this initiative, is to bring postdocs, right, they are working outside Brazil, back to Brazil, so that we can accelerate the pace here, right? And when I'm talking about national and international collaboration, of course, we cannot do everything here. And but there's lots of collaboration. If you apply, for instance, for a JP, which is a jovem pesquisador, is a younger research proposal. The idea is that you can collaborate with other groups in the state of São Paulo, in Brazil, but also outside, because you will not be able to do everything in-house. So this is the kind of thing that you're trying to foster here. You try to see if you can increase your networking, right? Your collaboration. This is something that is very important for this initiative. And this is strategic partnerships, for instance. They are very important as well because, as you know, we here we have been receiving different people, for instance, from the military as well. And in my lab in particular, and I know that here in physics, they also visit lots of different labs here. And what happens is that they are seeking collaboration, right? I know that it's very difficult sometimes to convince these people, but at least from the kind of conversation that we had with some, key persons from the Army, they say that they are very interested. There has been already some workshops happening in São José dos Campos, for instance, where they try to explain exactly what they are looking for. So this is something that is really important. And also, another thing is the infrastructure, right? Because if you want to do something that is in terms of new knowledge being brought to Brazil, you need infrastructure, right? And with this kind of research grant that we are giving out, like JP, and also these other two calls that are going on right now, the idea is that you can have a very good lab, right? You can run this lab here. And then with this lab, you can do, different experiments that we could not do here before. And you can create your own lab, right? And FAPESP is doing very good in bringing these ideas and these new concepts to this state. And this is thanks to this initiative, the CUTIA initiative. And another thing is the startups, for instance. This is something, that's why I keep telling you that in FAPESP actually was really very strong about it. We need to have engineers involved in all of these projects because you need to have this technology or any knowledge new knowledge being developed transferred to the industry. So you need applications, right? For instance, my area is in the field of telecommunications. Of course, in telecommunications, there's lots of new and interesting devices that when you talk about classical devices that we can do here in Brazil. But you need a lot of different structure if you want to take this, as I said, the quantum leap and do something that can be used for a quantum communications, for quantum communication. So in this case, you getting involved with the knowledge that we already have in all the engineering departments in this Unicamp or University of São Paulo or UNESP. You know that a lot of people are doing fantastic research. And the good thing is, from all the study that we have been doing in this initiative, we see that most of the research is basically dominated by optics applications. So the bridge is very close for you to connect these 2 points from going to classic to quantum application devices. So you have to take advantage of the knowledge that we already have in the engineering as well. All right? And also the diffusion of knowledge, but this is also important. And one thing that I need to mention to you, I was going to mention this later, but I was discussing with Emmanuel a couple minutes back, that one of the results, important results that we have from this initiative is that in the electrical engineering department here in this campus, we are able to create the first quantum engineering certificate. The quantum engineering certificate is similar to a minor in United States University. And that was, of course, was only true because of this strong collaboration that we have with this institute. So we have lots of fantastic professors here that are teaching some courses exclusively for this certificate. And this is fantastic because, you know, before the certificate, we had zero courses related to quantum mechanics or quantum stuff at any given level. It was mentioned only. Now we have a very strong structure that allows all the students to get in touch with this completely different world where you have access to the knowledge to develop new applications in quantum technology. And this, of course, I publicly here thank all the professors that participate in the elaboration of this, helped collaborate in this construction of this new certificate. And now, as I mentioned, we are taking a further step. We are now have a GT, or a work group, where we are now discussing the creation of a quantum engineering course here, right? And this is going to be a multidisciplinary initiative as well. That's going to involve not only the engineering, the engineering departments, particularly the electrical engineering department, which is leading the initiative, but also the Institute of Physics, the Institute of Mathematics, the Chemistry Institute, and in this, we hope with this thing, as happened in the certificate, which was the first quantum engineering certificate in Latin America. And we hope now to have the first, if everything goes well, of course, the first electrical engineering course in the Americas. So this is a very strong initiative. It's going to be a 5-year course as well. And as I said, it's going to involve everybody here in this campus. And let's see what happens. All right, but I want to talk a little bit about what happened in this trajectory of these initiatives. But I think it's very important to mention that quantum technology is not something that is new here in the state of São Paulo in particular. This is, of course, has been happening for a long time, decades actually. And as you see that you have all these different initiatives, some of them was created here in this institute. And but the main purpose of the QTIA initiative is to focus primarily on quantum 2.0, right? But of course, we will not say turn our back. If you have a very good and disruptive application, for example, they use this quantum 1.0, right? But quantum 2.0, that's something that has been happening for quite a few years, as you can see. And look at what, I mean, I just took this timeline here, starting at 2001, but of course something happened before that, but that's not the point here. But you can see that when everything started, say in 2001, you can see that, look at the amount of proposals that you have for this CMPQ initiative, where 17 proposals were contracted, right? Which is quite amazing. And also, if you jump a little bit further to 2009 and 2015, now with a joint proposal between CNPq and the FAPS, which is the research foundations, you can see that was able to create a consortium of 66 different researchers, which is quite amazing as well, right? In different states of the country. And more recently, from 2016 to 2022, another call for proposals between CNPq and the FAPS, was being contracted in 2016. Also create a different, like you said, CPOFs and INCTs, which is fantastic. And another thing that I want to call your attention is that even at that time, prior to the QTA initiative, you already have applications being developed in Quantum 2.0, which is fantastic. And this is just to tell a little bit about how the QTA initiative was created. And we have Professor Sérgio here, which was one of the leading researchers at the beginning of this initiative. But along with Professor Sérgio, we have Professor Frederico Fred, which was a professor here in the Physics Institute. Gustavo Wiederhecker, which is the coordinator of the QTA initiative. Professor Marcelo Terra Cunha from UNICAP. Gustavo Wiederhecker is also from UNICAP. Marcelo Terra Cunha also from UNICAP. Paulo Nussenswein. Paulo Nussenswein was actually the one who came up with the idea of creating this group of people called Quintech, right? Where the idea was to create a roadmap of quantum technologies for the state of São Paulo. And this was the embryo of QTA, right? After, I forgot to mention Philippe Courtet, which is also a professor here in the Physics Institute, was also part of this group. This is how everything started. And I joined the group a few years later, a couple of years later. And Professor Felipe Fanchini from UNESP joined the group as well later, 2023, if I remember. And what happened, how this group, what we used to do, we used to meet every week to discuss how this initiative was going to be created, the roadmap would be created, right? And then we have online meetings from 2020 to 2022. And I don't think, I think Celso, probably you were there in the workshop in São Paulo, Principia workshop, right? In São Paulo, we organized a major workshop on quantum technology. It was 3 weeks dedicated only to discussing how we could come up with a roadmap in quantum technology that could be adopted for, say, in the case for FAPESP. And then we had a lot of fantastic people from the state of São Paulo, from outside the state of São Paulo, and also from outside Brazil. Everybody joined together. It was a kind of immersion on quantum discussions, on what is the best approach that we could have to create our roadmap. Because I don't know if you feel familiar, but most of the countries, China, Russia, the European Union, United States, of course, Canada, Japan, all of them, they have their own roadmap for quantum technology. And as I said, when technology is involved, the engineering must be there. And we discussed all the roadmaps that are already available. That's lots of roadmaps. in order to come up with the best concept for the Brazilian, particularly the state of São Paulo roadmap in quantum technology, right? Australia also has a very nice one. And what we try to do is by the way, if you want, you can access all these roadmaps. They are published in journals, of course. They are publicly available. Or you can visit the web page of these countries when you look, for instance, for the quantum flagship in Europe, where you have the consortium of the European Union related to quantum technology. Although you have the consortium for the whole European Union, you also have the countries, some of the countries also, they have their own roadmap. And our roadmap was mostly inspired by the roadmap that they have in Denmark, which is, I'm sorry, in Netherlands, where they have a fantastic roadmap that covers everything, from quantum workforce to how you create or how you discuss the formation of this human resource, and what are the leading topics that you should pursue in a quantum roadmap that attends the needs of your particular country. So that's what the kind of thing that we try to do, is to understand what the abilities we have in the state of São Paulo in all lines of research, quantum research, in order for you to elaborate what this guideline should be, right? And then this, in 2023, there was in London, FAPESP Week, where was discussed among other things, quantum initiatives that FAPESP was trying to lead at that time. In 2023, after, you see, 3 years already that we have been meeting, online meeting, and discussing what our roadmap should look like, right? We had a total of 11 different chapters related to different topics of quantum technology in this roadmap. And then we gave FAPESP an executive summary of what the quantum scenario in the state of São Paulo should be. And was from that executive summary and the roadmap itself that FAPESP gave the okay to the creation of the program, FAPESP program on quantum technology, all right? Was in December 23 that was approved by the FAPESP Council. There's a mistake here on February to December 2024. Here it says the Young Research Award, FAPESP FAPERJ. Actually, it was just FAPESP at this point. The FAPESP FAPERJ came next year, the following year, actually. This was the kickoff of our first call for proposals. And the idea here was what we did. We chose 5 different proposals for young research, right? And in December 24, there was an open ceremony where we made this thing public, which was very good. And this today is when you look at the steering committee of the CUTIA, actually not the CUTIA, actually. These are the people, and all of these people, all of them, were here in the state of São Paulo during that workshop where we had this immersion to discuss what is the best initiative. And that was amazing. And after this, we created, we had to create the executive committee, which is coordinated by Professor Gustavo Wiederhecker, myself, and Professor Felipe Franchini. And what we do, we actually discuss how the proposals that we have are elaborated, the focus of the proposal, and of course everything has to be discussed with the scientific directory of FAPESP for, you know, lots of reasons. After all, they are paying the money, right? Anyway, and this is a map where you have different countries and the different amount of money that they are investing in quantum technology. I suggest you strongly that you take a look. And this map is clickable. So if you click on this map, you see from all different countries that are listed there, all the initiatives, the amount of money that they are investing. You see that in Brazil, I don't know if you can read it actually, it's 420 million Brazilian reals, which gives $79 million. I don't think this value is quite accurate. I think with this one, it doesn't count the 150 million reais that FAPESP is investing in Cutia. And in addition, I think, I don't know if all of you know that the Brazilian government, the beginning of the year, announced that they're going to invest 5 billion reais, which is roughly $1 billion in quantum technology. Well, the priorities are debatable because they said that most of the money is going to be invested in quantum computing, right? About 500 million reais is going to be invested in sensing, quantum sensing. So it's their choice, right? But in any case, if you come up with all this money, I think Brazil is very well positioned in terms of quantum technology investment, which is about half what Canada is doing. And Spain is about the same that we are investing. In this amount of money, it not only includes what you have for the investment in 2025, and it also includes what we have in the next 10 years, right? And this money that Brazil, the federal government is going to invest is until 2034, right? About 10 years. So that gives you a very good picture of what's going on here. So with that in mind, I think Brazil will jump a lot in that chart, as you see, compared to the other countries, right? All right, and another thing that's worth mentioning is that the global effort, as you see in 2025, is about $57 billion. Half of this money comes from China. And when you talk about the market for quantum technology, this until 2040, this goes up to close to a little bit over $100 billion. So that's quite impressive, right? And one thing that I would like to mention here, just because this is something that I extracted from when you click on Brazil. And this is an excerpt from the text that is there. And they textually mention what is going on here in this institute, which is quite fantastic, right? Okay. I have to mention that this, when it comes to numbers in this plot, in this slide, this number, of course, they are not updated. But it gives you an idea. This is until December 2024, but was the only thing that we are able to get at this point. And cloud is related to the titles of these, all the projects that you see in that chart. But one thing that is very interesting, when you take it into account thematic projects, you see that the vast majority of the money is being invested on thematic projects. And young researchers, look at the total, right? It's 210 million reais. 131 million just for thematic, 37 million for young researchers, right? And this is just for the physics committee in FAPESP. I'm not talking about all the other ones in engineering and anything. This, for this slide, is just physics. And young research, 13 million. PI, which I'm not sure if this is an initial project in FAPESP, 8.2 million. And the generation project, for those of you which are starting, I strongly suggest to take a look at this project in particular. So this is the kind of money that you can see right now being applied in FAPESP for the area of physics. This is a zoom in, let's say, when you take a look only at the projects for generation, PI, and JP. But all of these projects are strictly related to quantum technologies, right? So right now, FAPESP has about 46 million reais invested in quantum technology on these three kind of projects, right? So this is, as you see, JP is the leading one, right? And this is when we came up with the concept of what CUTIA should look like. We defined a few areas where we imagined that we would be worth investing money, right? So at least with this slide here, you have an idea of what is about to come in the future, right? In terms of what kind of investment or call for proposals you should expect from CUTIA. And a CPE, I don't know if you know, is a research center in engineering. Because, as I said, you need to have the ability to transfer all the knowledge that you produce to the industry. You need to have applications, so a CPE makes a lot of sense. Of course, the JPs, thematicals as well. We already have one, which is about to have the final result, hopefully soon. SPSAS schools, which is something that we discussed very much. This is something that is very important. As I said, the idea is for you to form people and try to bring people back to Brazil. With all the money being invested in infrastructure and the ability to bring our brains back to Brazil, we try to see if we can convince people, good people, to stay here and develop their research here. And these schools, I'm not sure if you're familiar with the concept of these schools, but this is very interesting. And it's something that we're really looking forward to having. PP projects, this is important because it means that you're going to do something that is very close to being applied in the industry, right? Postdoc scholarships, PAIP, which is a program for support infrastructure, particularly multi-user structures. This is very important. Well, this is the schedule call for proposals, but the first one, which is in gray, that already happened, right? This is already been implemented, and we already have now the FAPESP for PERGE joint grant, where the idea, as you see, is to give out 5 of these grants, right? 6 million reais grants, and we expect to have the final result on February 2026. And there's another one which is also going on, which is the consortium. And this one are 3 grants is going to be approved, and they are about 10 million reais, right? And this is just to mention the first one is a JP, and that's why JP is has such a large part on that slice, right? Or the slice chart that you see. And this, I think, Amilson is here, right? And we have all these 5 first grants that were approved, and which are already going on, which are all of them fantastic projects. And I hope Amilson is having a very good time here in São Carlos. And we are looking forward to seeing actually nice results from this project, all of them. And this is just a little bit more information on these projects, as you can see, because this is very important. Sometimes it's very frustrating when you look at the call for proposals from FAPESP, is that, well, let's say that the call for proposal is 5 million reais. And all of the extra attachments that comes with the proposal, let's say the technical reserve, let's call it this way, complementary benefits, and so on and so forth, they usually are embedded in this money. Depending on the call for proposal that we are trying to do, we are putting this thing outside the budget. So let's say if it is 3 million, you can, the technical reserve, complementary benefits, this is all going to the side. If you need 3 million, you have 3 million. And the scholarship and stuff is not accounted or taken into account in that 3 million. And that helps a lot. But that cannot be done for all of the kind of proposals, right? And if you take a look at FAPESP, FAPERJ, which is 3 million, well, when you look at this money, it's not very much, right? If you think for a moment. But it's 3 million for both sides. And when you submit the project, you have to make sure that the partner that you're going to have in the state of Rio is going to be a very good one that you can rely on, that can complement the kind of research that both are doing, right? Because each one is going to receive 3 million. So the project has to be, the proposal has to be the same, right? Both has to be approved in order for you to get this kind of support. And the good thing, at least for this one, all of these things that comes besides the budget, you don't have to take into account in the 3 million, as you can see there. The FAPESP consortium, the idea is to fund 3 10 million reais proposals. And bear in mind that everything that I'm talking about here comes from the Cutia budget, all right? So the FAPESP Research Consortium is going to fund 10 million reais, but unfortunately in this one, everything has to be included in this 10 million. If you need a scholarship, it's going to be there, right? So, not for our choice, by the way, because we can do a lot of things when it comes to how you write the proposal, but it's FAPESP that decides what can or cannot be done, all right? And the consortium works like this. The concept is interesting. That had some, tricky things there. In order for you to submit this thing, you need to have an active project going on in FAPESP. And one thing that I particularly didn't like very much is for instance, when you consider the associate researchers in this project, which you can have up to 10. But these researchers, they need to be outside the academia. And sometimes it's very hard for you to find researchers that do not come from the academia. right? They are only in the industry. And we actually tried to see if FAPESP could change that. And I hope they did, actually, right, in the end. Also, you need to be, you can qualify in this project. This is going to be outside the project. If you can be eligible to international visits, like, if you're familiar with the sprint format, you do fine. And as I said, another thing, important thing, is that you can involve, if possible, the military, right? We are doing, at least in my lab, we are doing some of the research that we are doing involves Embraer, for instance. They have, Embraer has a subsidiary called Embraer Radar. And the kind of thing that we are developing target this kind of application as well, but using quantum technology. So, and the idea is that once you reach to this kind of companies, it gets much easier for you to get the contacts, the right contacts for you to go to the right militaries, right? So the kind of application that we are developing, including the possibility of embed quantum sensors in drones, for instance. This is something that we expect to do already next year. We're going to have a drone from ExMobile, so it's a military drone. So with this one, we expect to get closer to the, surprisingly not the aeronautics, but with the Army, because they are the ones that monitor the frontier. So this is, as I said, I mean, it's very important that you also try to see if you can develop things that can be dedicated to defense. And just to mention another kind of support, for instance, FINEP released a call this year. We submitted a proposal to this call, and we focused only on defense for quantum applications, right? And we're 2 proposals behind the limit. We're approved, but we are 2 proposals behind the budget. So if FINEP gives us supplement of this money, we may be able to get our proposal approved as well. But it's only dedicated to defense. So you see that right now in Brazil, this is something that is very important. You really have to start looking at what's going on in terms of defense. This is how the FAPESP proposal is going to work. You have one PI, one co-PI, which in our case, if you submit, is going to be the co-PI in the state of Rio, and associated researchers from the state of Rio de Janeiro. And as I said, this one is going to be a 3 million reais, right? And I think everything else here already discussed how it's going to be, right? And we expect to select 5, and I hope we have 5 good proposals as well for this one. And I think probably this slide is the one that you're looking for to see in this presentation. And the point is, I don't have the answer for when the call for proposal is going to happen for all of these ones listed on this slide. That's because it's up to the scientific directory, FAPESP scientific directory, to decide. And we hope to have this definition until the end of this year, worst case scenario, beginning of next year. So we're going to open the first call of proposal for 2026. And as soon as we have some news, I can communicate Emmanuel, and he can spread the news to you, so at least you have an idea. But I can guarantee you there's going to be at least one. The scientific director is saying that we're going to have only one big proposal. So let's see. We have to hear from them in order to decide exactly what's going on. But although this is a little bit frustrating, but I think that the seeing the glass half full, I think we're still doing fine. And the program is up and running. I think we're receiving fantastic proposals. And we are still hoping that we can bring more people from that are abroad back to Brazil. All right. So at least in terms of I would like to tell you today, this is it. And if you have any further question that I cannot answer right now, if I don't have any information, I can send the question to Gustavo, which was not here because he's in Europe at this point. And but I'll be glad to send your question, any questions you have that I'm not able to respond, to discuss with him and see if we can have some feedback also from FAPESP. All right? So I'll stop here. Thank you very much.
Thank you, Benio. Do we have questions?
Thank you for your nice presentation. I have two questions. One is about long term, and another one the short term. So, do you think about an education and extension, project to teach the kids some simple concepts about quantum mechanics? And another one, the second one, have you think about creation of technological center for quantum technologies?
Sandwich?
No, it is a technological center, an ICT.
Look, regarding the first question, well, in my department, actually, we are about to create this year, which something that I have discussed since the very beginning when I came to this institute to discuss about the creation of the quantum engineering certificate, which was in 2023, was the extension, is an extension course called Quantum Literacy, right? Letramento Quântico, which is going to be offered to the public schools in São Carlos, right? So this is something that we are going to have already next year.
Maybe in the form of videos, single experiments.
Well, this is, yes, exactly. I just don't know if you're considering that CUTIA is going to give any support to this one. And the answer is no, because the CUTIA is for research purpose only, right? But all the infrastructure we are going to develop in our department, and if we can partner with another professors here in the IFSC, that would be great as well. But that's the idea. Now, regarding the second question, which is for if we support the creation of an ICT, right?
Yeah, because at least for me, the university here, we have research focused on theory, basic theory. So for me, if you create a technological center, an ICT, though you are more able to transpose the science to the technology.
I see.
If you have a center focus on quantum technology, not science, but more technology than science in the center.
Well, I think the answer to your question is that Professor Vanderlei created, which I think officially is going to inaugurate this month or next month, I don't know, the Center for Quantum Technology. I'm cutting the name short, but it's essentially a center for quantum technology,
yep,
where they're going to have an infrastructure at the campus too, where I mean, and also Professor Vanderlei was able to get 10 million reais support from the rector of the University of São Paulo, which is going to be invested in the infrastructure of this one. So it's going to be focused on quantum technology. And I'm extremely happy about that, because this is the kind of subject that I have been discussing with my colleagues, Professor Daniel, Professor Sérgio Muniz, that it's about time that we have something of this magnitude. And I was very fortunate to hear that Professor Vanderlei went exactly in that direction. So this is about to happen. I think as soon as the building is completely...
Yes. At least for me, if you have a place, then you are more able to join the people around there.
Well, I think that's the whole idea, right? And since you're here, you can talk, Euclid is right there. I mean, you can talk to him and see what kind of space is going to be dedicated to, or Professor Daniel. And you see, I was able to pay a visit to how the building looks like today, and I was impressed. Everything is pretty much done. Of course, Euclid can give an update on that. But I think the infrastructure is absolutely fantastic. And by the way, since it's a multidisciplinary initiative, and myself, for instance, what I can tell you is that all the research proposal that we are submitting are intended exclusively to build the infrastructure for quantum characterization in that facility. So I can answer your question with 100% certainty. That's what's going to happen. That's the idea, actually.
It's nice.
I have a question. You mentioned several times the Young Researcher Program to bring back to Brazil
Yes.
outstanding young researchers to work with quantum. And I remember a program from the Humboldt Foundation in Germany, where they had this kind of young researcher program, but they had also a program for senior researchers from abroad that they were bringing. So they were really hiring established researchers from leading places abroad to bring them to Germany for like 5 years with full support. Is that on Cutia plans? Do you know anything?
Well, the problem is the kind of support that we're going to have is pretty much the one that I listed. It has to be on this thing. Sorry, a second. It has to fit on this one. And if you have, because I know that in Germany they have a very different, let's say, way of dealing with when you have a senior professor or professor that retired. You can correct me if I'm wrong. But because in my department we received a professor from Germany which retired, and then all the connection that he has with the university simply disappeared. And then it's very interesting for them to come, for instance, and they do that, to underdeveloped countries to help with whatever capacity they can, which I think in that time we got money from the university, not from FAPESP. But I don't think that this program will focus on bringing foreign retired professors, for instance, or senior professors, because the idea is to bring young researchers, essentially, and try to make sure that they stay in Brazil. Right? And I do hope that Amilson doesn't go back.
Me too.
Stay here, right?
We all hope a lot on Amilson.
Okay. As I know, FAPESP is working in a full administrative capacity. So many of these programs that you mentioned in your presentation, they will not be implemented because they don't have capacity.
Yes.
Like these EMU equipments, they don't have capacity to implement this. This is what I know.
I know. Yeah, that is why I mentioned that in order for us to make another big
No,
call,
they put their announcement in 2025. This will
no,
not happen.
because
here.
this was the idea. It's not going to happen, but I can guarantee you one thing, Euclides. We're going to have one major call next year. And that's the only thing that we could extract from FAPESP. One call. Big call. Yeah. This, because FAPESP is not going to make anything larger than that. Exactly for, as you mentioned, the limitation that they have already. But we expect one. What is up to us to decide, and that's why the committee, the executive committee, has to convene this year. Worst case, beginning next year, is to decide which one we're going to open first. I mean, if you want to hear my personal opinion, I think the EMU would be fantastic. No, yeah, but the idea, or JPs, for instance, the idea was to have JP calls every year. But I'm not sure that we're going to. Yes. Well, that's the second year of QT, right? Right. No, yeah. This was what we designed at the beginning of the QT. This, of course, is going to be rechanged, remodeled so that we are able to accommodate whatever we can do according to FAPESP demands, right? Because it's, as I said, the money that is going to be separate for any one of those things is up to the scientific director to decide, right? It is not up to us, not up to the executive committee, unfortunately. But I think it's going to happen. One, at least, I can guarantee you. Maybe no, I'm telling you it's going to happen.
I don't see further questions. So I would like to thank you again, Bennu, very much for your time and your talk. Thank you. Our final speaker had a personal problem, so he will not be able to come. So I think this is the end of our workshop. And before I end, I would like to thank my partners in the organization, Celso, Daniel, and Vanderlei, all the technical staff, Chitão and Michael up there, everyone that helped in the Vanderlei amazing class yesterday night, and all the speakers that were amazing for us the last 3 days. So thank you very much. We see you in another opportunity.